Hello and welcome to lecture 26 of our Essentials of Semiconductor Device Physics course. In this lecture we start looking at p-n junctions, which are the building blocks of electronic devices. So in the previous lectures we learned that when we p-dope a semiconductor, we increase the concentration of holes and decrease the concentration of free electrons, and the Fermi level goes down. And when we n-dope a semiconductor, we increase the concentration of free electrons, decrease the concentration of holes, the Fermi level goes up. And in this lecture, we want to analyze what happens when we take a piece of semiconductor and then we p-dope one side and dope the other, forming this way a p-n junction. So if you do that, we're going to have a system that is out of equilibrium because this part of the system has a high concentration of free electrons, a high Fermi level, in other words, a high chemical potential, and the system on this side has a low concentration of free electrons, a low Fermi level, in other words, a low chemical potential. So we have already encountered a very similar situation in lecture 9. In lecture 9, we also analyzed a system that was very similar to the p-n junction. So we already know what's going to happen. Electrons will diffuse from the region with high concentration of free electrons, high chemical potential, to the region with low concentration of free electrons, low chemical potential. But recall that before we form the p-n junction, if we analyze only an n-doped semiconductor, recall that in the n-doped semiconductor there's an array of ionized atoms. These are the impurity atoms that donated an electron. Each one donated an electron to the conduction band. If they donated an electron, they became positively charged. So we have an array of positive ions in the n-doped material. But the charge of these ions, they are covered by the free electrons that are moving around in the semiconductor. So these charges do not appear. But when we form the p-n junction, now there is diffusion of some of these electrons to the other side. So these electrons that diffuse to the other side, they now uncovered this charge. So this charge now appear. So we have an accumulation of positive charge in the n side. Recall that these charges do not move, they are the ions. So these charges do not contribute to current, but they will contribute to the formation of an electric field like we discussed in lecture 9. But the main difference between the p-n junction and the system we analyzed in lecture 9 is that now we also have holes. So holes will diffuse from the p side to the n side because there's a high concentration of holes in the p side and a low concentration of holes in the n side. So holes diffuse from the region with lower chemical potential to the region of higher chemical potential. It's the opposite way of electrons because holes are actually an absence of electron. So when we consider that there is also diffusion of holes from P to N, these holes will also expose the negatively charged atoms in the p-doped side. So these negatively charged atoms, now their charges are exposed. So we have an accumulation of negative charge in this side. So if you have an accumulation of positive charge here and an accumulation of negative charge here, then there is the formation of an electric field as represented by the black arrow, just like in a capacitor, just like we discussed in lecture 9. Now if there is a formation of an electric field, then there is the creation of a drift current because the electric field imposes a force on the charge carriers, creating a drift current. For example, when electrons are trying to diffuse from N to P, the force is in the opposite direction of the electric field, so it's in the direction of P to N, so the electric field pulls the charge back, pulls the electrons back. And this current caused by the electric field then is in the opposite direction of the diffusion current. And of course, equilibrium will be reached when these two currents compensate each other. And we need this condition for both electrons and holes. So there are actually two conditions for the equilibrium. The drift current of electrons has to compensate the diffusion current of electrons, and the drift current of holes has to compensate the diffusion current of holes. So there are actually two conditions here, one for electrons and the other for holes. And we also know that now there is an electrostatic potential associated with this electric field, and equilibrium will be reached when the electrochemical potential, in other words, the Fermi level, is constant across the material. So the electrostatic potential associated with this electric field will, in equilibrium, compensate the difference in chemical potential. The chemical potential on this side is higher than in this side, so this electric field has to lower the energy of this side with respect to the energy of this side until the Fermi levels align. Okay, so now we're ready to analyze the band structure of a p-n junction in equilibrium. So this is a drawing of the band structure of a p-n junction in equilibrium. In a drawing of this kind, we usually show energy in the vertical axis and space in the horizontal axis. So this line here is the beginning of the conduction band. So all energies above this line would be energies inside the conduction band. And this line here represents the top of the valence band. So all energies below this line are energies inside the valence band. And we need to have this drawing with a space dependence because the band changes as we walk across the p-n junction. As you can see, the band bends, and we're going to analyze why this happens in a few minutes. So you can understand this side here as being a copy of this band structure, but showing only the top of the conduction, the bottom of the conduction band, and the top of the valence band, and the Fermi level. So this line, and this line are copied over here. And the same on this side, you can understand as being a copy of this line, and this line over here. So why is this band lowered with respect to this one? We already know why it's lowered. Before the p-n junction was formed, the Fermi level here can be interpreted as being only the chemical potential because there is no electric field in this story. So there will be a diffusion of electrons from N to P and of holes from P to N, like we just discussed. And then there will be the charge will be exposed of the ions, and there will be the formation of the electric field. So there will be a new energy in this story. It's the electrostatic potential energy due to the electric field. So now, after the junction is formed, the Fermi level is the electrochemical potential, is the total potential. It's no longer only the chemical potential, just like we discussed in lecture 9. So if there is a new potential, then the energy changes. For example, this energy here is equal to this energy minus the contribution of the electrostatic potential due to the electric field. And it's lower on this side than on this side because this is a band structure for electrons, and the potential energy of electrons is lowered in this side with respect to this side due to the electric field. An intuitive way of finding which part is lowered with respect to each is to imagine that you drop an electron here in this region where the electric field is. The force of the field is in the opposite direction of the electric field, so the electron will be pulled in this direction. So the electron is going from the higher potential to the lower potential. So the higher potential is on the P side and the lower potential is on the N side. And another way of understanding this is to recall that the condition of equilibrium is that the Fermi level, the total potential, must be constant. So if the Fermi level is higher on the N side than on the P side before the junction was formed, then in equilibrium they must be constant, so this side has to lower with respect to this side. And they will lower until the lines align. So now we have only one Fermi level, so we use only one symbol for it. So if this band will lower with respect to this band, then it means that inside the region where the electric field is, the band is bent. And the physical origin of this bending is just the work done by the electric field. So you can understand that you have an energy here, and here there is no electric field, so the band is constant. And now if you compare this point here, for example, and this point, there will be a difference. What is this difference? Is the work done by the force exerted by the electric field. So it's as if we had lowered, if we were talking about gravitational energy, for example. And in a few minutes, I'm going to show you a mechanical analog of this bending. But you can understand that this is just the work done by the electric field. And since the electric field is confined in this region, then the band is bent only in this region. So we have a band diagram. Recall that this band diagram is in units of energy. So electrons always go from the region of high to the region of lower potential energy. So this region here has a lower electrostatic potential energy with respect to this region, but has a higher chemical potential in this side with respect to this region. The concentration of electrons here is higher than in here. So the lower electrostatic potential in this region compensates the higher chemical potential so that the total potential is constant. And this equality here is just the statement that the electrostatic potential difference exactly compensates the initial chemical potential difference. We have already seen basically an identical relation in lecture 9, but instead of showing the chemical potential difference in terms of the initial Fermi levels, we use the symbol mu in that occasion. But this is the statement that the electrostatic potential difference, in other words, how much the band was bent, compensates the initial chemical potential difference. Now notice that if we were to plot the potential in units of volts, then in units of volts the potential is higher on the N than on the P side. But because electrons have negative charge, when we convert from volts to units of energy, then this higher potential will become a lower potential. It will be negative with respect to this side here, which I set to 0 just to have a reference. So in terms of volts, the potential in this side is higher than in this side. In terms of units of energy, is lower on this side than on this side, like shown here. Now, if you are still a bit uncomfortable as to why the band bends in this region, I'm showing here an analogous situation, but using gravity, because gravity is always more intuitive than electric field. So suppose that this drawing here is you, and you are lying down, and I'm drawing here the internal energy of your body, so the sum of all energies of all atoms and molecules in your body, as a function of space. And I'm drawing here a high energy for the head, because I know you're a very, very clever person. So this will be a drawing of internal energy as a function of space. Now suppose that instead of lying down comfortably, you lean like this. You are still the same person, so your internal energy has not changed. But it has picked up a contribution from gravity now. Now your foot still has the same energy, but your head has a higher gravitational energy with respect to the foot. And the gravitational energy increases linearly. So what's going to happen in this case? Your internal energy will be bent due to the contribution of gravity. So you can understand that this value here is the initial value plus the contribution of gravity. This value here is this value plus the contribution of gravity, and so on. It's the same idea here. This value for the beginning of the conduction band is this value of the beginning of the conduction band plus the contribution of the electrostatic potential. It's exactly the same physics here and in here, just the nature of the force change. Here is gravity and here is the electric field. Now, to conclude our qualitative analysis of a p-n junction in equilibrium, let's again resort to an analogy using gravity. So suppose that we have a region here. There's no gravitational potential difference, so it's flat. But in this side of the region, we have a high concentration of balls moving everywhere. So the random movement of the balls represent the thermal movement of electrons in the n side. So the balls here are electrons in the n side, and since there are no electrons in the p side, I'm showing here a region without balls. So of course there will be diffusion of balls from this side to this side. But now suppose that this system is a bit magical, and as the balls diffuse to the other side, there is an increase in the gravitational energy of this side with respect to this side, until no balls can reach the other side. So the gravitational energy increases until the flux of balls to the other side ceases, stops. So this is analogous to the p-n junction in equilibrium, and this is analogous to the p-n junction before equilibrium was reached, just after we formed the junction. In this case here, now we have a diffusion of balls from this side to this side, but we also have drift of balls from the top to the bottom due to the gravitational energy difference. In other words, gravity pulls the balls back. And the flux upwards due to the diffusion is compensated by the flux downwards due to gravity, in such a way that the net flux is zero. So we have both a difference in gravitational energy, like we have here a difference in electrostatic potential energy. We have a difference in chemical potential, we have a difference in concentration, like we have a difference in concentration. But the total potential, the sum of gravitational and chemical potential, is constant in this system, like it's constant in here. We still have diffusion of balls going up, we still have diffusion of charge from n to p and from p to n. But we also have drift downwards, and we have drift from n to p and from p to n in the opposite direction of diffusion. So electrons will diffuse from n to p, but they will drift from p to n, and holes will diffuse from p to n and drift from n to p. So the total current is zero, even though there is a current of diffusion and there is a current of drift. So this system here is analogous to the p-n junction in equilibrium. Okay, so with that we conclude our qualitative analysis of a p-n junction in equilibrium. I hope you noticed that this is exactly the same physics we discussed in lecture 9, with the only addition that now we have also transport of holes. So in the next lecture we're going to begin a more mathematical analysis. Our first job will be to prove this identity, and then we're going to use this identity to prove what we already expect. So we're going to prove this identity here rigorously, invoking the condition of equilibrium for currents. So I see you next time.